Hey everybody, it is Wednesday night. I promised a video late this afternoon. I was supposed to get a delivery from a Home Depot truck today that was supposed to come between 11 and 3, and it didn't come until like 5:30. So I was waiting around all day for it and working in the yard, and figured I would record my lecture after the Home Depot truck came, and it didn't come. So it's about 7:30 at night now, and I'm recording my lecture for the day. But it's going to be really short. I'd be surprised if we hit 15 minutes on this one, because it's on a topic that's basically about empty space, which is the topic of the so-called interstellar medium. Trying to get my light a little bit better right now. The interstellar medium is a fancy way to say the stuff that is in between the stars, interstellar. And you might say, well, isn't there just nothing between the stars? Isn't it just empty space? It's not entirely empty space, and that's why it's worth saying a little bit about. When we look at the Milky Way galaxy from the inside, remember, when we're looking at the Milky Way galaxy and we see these dark spaces, that's not necessarily places where there aren't any stars. It's places where our view is being blocked by hydrogen gas clouds and gas and dust within the Milky Way galaxy. And particularly in the spiral arms, there's more gas and dust than in the outer halo. So we know that there's stuff between the stars in the galaxy and us. We know that even when looking at the stars we can see, because the interstellar hydrogen gas and dust and stuff affects starlight. And the farther away stars are, the more we see starlight affected by this interstellar medium. Just like when you are driving in the fog and you look at car headlights, that light is scattered by the water particles, water droplets in the fog. The material in the interstellar medium scatters light. That has the effect of not just dimming the light, but also reddening the light, because scattering is more effective at shorter wavelengths. So shorter wavelengths are bluer wavelengths, right? On Earth, the reason that sunsets look red is because the atmosphere of the Earth, the nitrogen and oxygen molecules that make up our atmosphere, scatter the light. Short wavelength light is scattered more than long wavelength light. So blue light is scattered more. That's why the sky is blue, because the atmosphere scatters that blue light more than it scatters the yellow and green and orange and red light. The reason that a sunset looks red is the sun, we're looking at light that's been traveling through more atmosphere. When you're looking at the sun low in the sky, it's traveling at an angle and passing through more of the Earth's atmosphere. Most of the blue light has been scattered out of that light, leaving behind red and orange and yellow. So we're familiar with scattering here on Earth. That same scattering happens in interstellar space. So because more blue light is scattered, the spectrum that we receive from distant stars is somewhat reddened. In other words, the blue end of the spectrum is somewhat reduced in intensity because some of that blue light has been scattered. We can just use this fact and compare the light from stars at different distances away from us to estimate the density of the interstellar medium, how much stuff there is in between the stars doing that scattering. So we can look at this reddening as it's a nuisance, because it gives us a less pristine view of the light from distant stars, but it's also a useful tool. And we have been able to deduce from this, well, hold on a second, before we take the next step. The other thing that happens, though, as the light passes through the interstellar medium, is you've got light passing through a relatively cold, low density gas. And we know that one of the things that can happen when you've got light passing through a cold gas is that that gas can absorb, not just scatter light, but absorb particular frequencies of light, particular wavelengths of light that correspond to particular energies, the energies that correspond to the differences in energy levels in that atom. That creates what's called an absorption spectrum. So the spectrum of light given off by the star can be affected by additional absorption lines caused by the absorption of certain wavelengths of light in the interstellar medium. So we are always trying to kind of disentangle these two effects from one another. So we can learn not only how much interstellar medium there is, but what it's made out of by studying the absorption spectrum of the interstellar medium. When we do this, we reach the not at all surprising conclusion that the interstellar medium is mostly hydrogen gas. Everything is mostly hydrogen gas. Hydrogen gas makes up 90-some% of the atoms and molecules, or atoms in the universe. The density of the interstellar medium is roughly, give or take, it's obviously more dense in some places than others, but roughly 1 atom of hydrogen per cubic meter. Imagine a cube that's 1 meter by 1 meter by 1 meter. In interstellar space, every cube that size has about 1 hydrogen atom in it. So the density is incredibly low compared to the density of what we think of as, even air, right? A cube of air that's 1 meter by 1 meter by 1 meter has a trillion molecules in it here on Earth. In interstellar space, it has 1. But that's not nothing, especially because there's a lot of space between us and even a relatively nearby star. So we can observe the effects of this interstellar gas as well. The interstellar medium is about 90% hydrogen, 9% helium, and 1% everything else. Carbon, nitrogen, oxygen, iron, magnesium, whatever. The other thing present in the interstellar medium are dust grains, little mineral, solid bits of mineral, the size of literal household dust. Interstellar dust has a composition not too different from what you'd find in an asteroid, silicates and iron and things. And there's also little bits of ice, carbon dioxide ices, water ices, nitrogen ices, that sort of thing. So very similar to the composition of a comet, right? We had this kind of dirty snowball model of what a comet is made out of, a combination of minerals and ices. This shouldn't be surprising because after all, the interstellar medium is what the solar system ultimately was formed from. Places where the interstellar medium is more dense collapse together into these denser gas clouds, which collapse into planetary systems. So the composition of the interstellar medium is interesting to us because it tells us something about the composition of the material out of which the solar system was formed, just like the composition of comets and the Kuiper belt and the Oort cloud is of interest to us because it tells us something, or could tell us something, about the composition of the material that the solar system formed from. This is a typical chunk of interstellar medium. Obviously, it's not from interstellar space, it's from interplanetary space. It's something we gathered within our own solar system. It has a size about a micron, a micrometer, a millionth of a meter. So very, very tiny bits of mineral dust. I said that there's not much interstellar medium in every cubic meter, right? About an atom in every cubic meter, maybe 1 dust grain in every cubic meter of space. But there's an awful lot of space in between the stars. Remember, stars are anywhere between 4 or 5 light years apart, or 10 to 20 light years apart. A cube that's 100 light years this way, and this way. So that's what 100 times 100 times 100, that's 1,000,000 cubic light years. Probably only has a few dozen stars in it, but it's got lots of empty space. And that empty space isn't exactly empty, right? There's a hydrogen atom or a helium atom or a dust grain in every cubic meter of that interstellar space. It turns out that the mass, excuse me, in our galaxy of the stuff in between the stars, the stray hydrogen and helium atoms, the little bits of gas and dust and ice, is roughly equal to the mass of the stars. In other words, there's the same amount of stuff between the stars as there is in the stars. So if we're asking what's the mass of a galaxy, which we'll be asking this really important question in a couple of weeks, you have to add up the mass of the stars, but you also have to add up the mass of the stuff in between the stars, and those are roughly equal. So about half the mass of a galaxy is, well, let me be careful because we haven't talked about dark matter yet. About half the visible mass of a galaxy is stars, and half the visible mass of the galaxy is the gas and dust between the stars. So the interstellar medium is important in some, the one way to think of it is it's just as important as the stars, right? There's just as much stuff between the stars as in the stars, so we shouldn't neglect it. NASA tried a mission to sample bits of interstellar dust, and obviously it's not exactly interstellar dust because we're not leaving our solar system. It's interstellar material that's moving through our solar system. And that was called the name of the mission was the Stardust mission. It was not a complete success, and I haven't checked lately to see what they learned from the Stardust mission. This might make an actually, either I'll put it in the discussion group or I'll sign it as a homework assignment to go do some research and figure out what the Stardust mission discovered. But the Stardust mission was a satellite with panels coated with little squares of this material called aerogel. Aerogel is a really cool material that is such low density that it is nearly transparent. It's translucent, but it's extremely, extremely light. One person described the experience of holding a piece of aerogel as being like holding solidified air. It's so light that I mean, here's a picture of it. The edges are actually fuzzy. It looks blurry because the density of the material is so low around the edges. But because it's got so much, first of all, it's also really, really strong. Here's a picture of a large piece of concrete sitting on top of a brick of aerogel about the size of a kitchen sponge. So it's strong in compression. You can break it this way easily, but it's sturdy in compression. It also has really interesting thermal properties because it's mostly empty space between the atoms. It's a very poor conductor of heat, and there's all these examples of holding a flame of a blowtorch underneath a piece of aerogel with meltable or flammable things on top of it. And the heat doesn't pass through it because there's so much empty space in the material that it doesn't conduct heat very well. So it's just really, really cool stuff. And the idea behind the Stardust mission is we would put these pieces of aerogel in like a big, almost like kind of like a solar panel. And we would just float it around in space for a while. And the density of it is so low that materials of interstellar medium would hit it and they'd go through the holes and they'd get trapped in it. So the aerogel would be like a kind of a sponge in space gathering up chunks of interstellar dust. Here is a picture of one of the panels of the Stardust mission. Every one of these is about the size of a brick. And we shot it up into Earth orbit and we floated it around for a while. This is what a little piece of cosmic dust, a little micrometeorite, maybe the size of a grain of sand, looks like trapped in the aerogel. And the idea was we'd fly this around for a couple of years. We'd bring the panels back to Earth. We'd take these little micrometeorites out of the aerogel and we would study them in the laboratory. Except that when we tried to bring it back to Earth, the Stardust mission actually crashed on the ground on the Earth, contaminating most of the samples that we had gathered with Earth material. Now there's no way to tell the material that came from crashing into the ground on the Earth from the material that came from space. I think they were able to salvage some of the samples and do some analysis of the material, but I'm not sure we learned anything important about the interstellar medium from the Stardust mission, but it would be worth checking out its Wikipedia page and then going from there to the NASA page for the mission and see if that's still up and see if they tout any discoveries that they made about the mission. But here's again a piece of micrometeorite, again about a micron across, a micrometer across. And it looks very much like a slice of an asteroid. If you've ever seen an asteroid up close. I know if you've ever been to the Air and Space Museum up in Washington, D.C., they have some meteorites and asteroids that you can go up to close and touch. It looks very, very similar to those. I think that's it, right? I think that's all I want to say about the, oh no, there's one more thing I want to say about the interstellar medium, which is, remember I said last time that we live in the Milky Way and we think the Milky Way is a spiral galaxy. but we can't see the spiral structure of the Milky Way galaxy from the inside because our view of the galaxy is blocked by all the other stars in the galaxy and all this other gas and dust in the galaxy. So how do we know that we live in a galaxy with spiral arms if we can't see these spiral arms? A lot of that information comes from observing the interstellar gas, the hydrogen gas between the stars and the gas clouds that exist in the galaxy, in the disk of the galaxy. And the way we do that is by looking at light that goes right through the interstellar medium, which is radio waves. Remember I said that scattering by light happens mostly with high frequency, short wavelength light. Blue light gets scattered a lot. Purple light gets scattered a lot. Ultraviolet light gets scattered a lot. Things like microwaves and radio waves, which have a long wavelength, the wavelength of a few centimeters to several meters, don't get scattered by interstellar gas and dust. They just go right through it. Just like radio waves don't get bothered by the Earth's atmosphere. That's why we use, or that's why we can use radio waves to communicate, because radio waves go right through the air and the air doesn't bother them at all. We also know about electromagnetic radiation, that high energy things give off short wavelength, high energy light, and low energy things give off a long wavelength, low energy light. Well, the interstellar gas and dust between the stars is cold. It's the temperature of the vacuum of space, close to absolute zero, which means it's not going to be giving off much light. And if it does give off any light, it'll probably be things like radio waves. There is a particular radio emission from hydrogen that is extremely useful in astronomy. Most of the light that we see when we're doing spectroscopy comes from electrons jumping around from one energy level in the atom to another. They can absorb light and go up a level. They can go down a level. They can give off light. That light tends to be in the visible spectrum, a little ways into the infrared, a little ways into the ultraviolet. But there's this other thing that electrons can do. And it's only important when the energy of the atom is really, really low. So the electron's not jumping around from one energy level to another. It is just sitting in its lowest energy state. But electrons have this property called spin, which gives them a little magnetic field. You can think of electrons as being like little magnets. And you can think of this thing that happens to electrons, like what happens if you take two magnets and you set them next to each other with their poles. Well, you set them next to each other with their poles in the same direction. So north poles here and south poles at the bottom. And you move them close to one another. They will sit there for a while. But if the magnets are very strong, or if you move them too close to one another, what will happen is the norths will repel one another and the souths will repel one another, and the magnet will flip so that and then they'll stick together. Because the North Pole wants to be with the South Pole and this South Pole wants to be with this North Pole. And so that flipping of two magnets due to their magnetic force between them is those magnets going from a state of high energy to a state of lower potential energy. The electron in a atom, let's just say a hydrogen atom for the sake of argument, because the interstellar medium is mostly hydrogen. So hydrogen atom is one proton, one electron. The electron has a spin, has a magnetic field. The proton has a spin, it has a magnetic field. When the electron and proton have their magnetic field in opposite directions, they are in a state of high potential energy, and those magnetic fields want to flip. When that happens, the electron gives off a tiny little bit of energy, just a tiny little bit of energy associated with the potential energy of its spin in the magnetic field of the proton. This really, really low energy light is always the same energy, because every proton and every electron have the same magnetic field. So when one of them flips, it always gives off light of exactly the same energy. That energy is a radio wave with a wavelength of 21 centimeters. So cold hydrogen in the depths of interstellar space is constantly absorbing and emitting this 21 centimeter radio wave radiation. Which means if we build a radio telescope and we tune the frequency to see 21 centimeter radio waves, we will be able to see all of the hydrogen gas in between the stars of our galaxy doing its thing. And we can create a map of where all the hydrogen gas is in the galaxy. Here is a picture of the sky taken in 21 centimeter radio waves. Remember, you have to be careful the way you use the word picture in astronomy. This is a map of the intensity of radio waves with a wavelength of 21 centimeters looking all around the sky. That stripe you see across the sky is the Milky Way galaxy. Okay. The reason it's brighter there in radio waves is because there's more hydrogen gas there than there is when you look north and south out of the galaxy. This is how we're able to map the galaxy and know that it is a spiral galaxy by using 21 centimeter radio waves. By mapping the interstellar gas, the interstellar hydrogen gas, we're able to figure out how dense the hydrogen is in different areas around us and able to create a map that places us within one of the spiral arms of the galaxy. And we're able to kind of deduce or infer the structure of the spiral arms of the galaxy from the inside by observing these radio waves. So a really, really important tool for astronomers, a kind of different kind of spectroscopy. It's not the ordinary kind of spectroscopy where we look at electrons jumping from energy levels and giving off visible light. It's one little energy shift that an electron and a hydrogen atom can do that always gives off the same wavelength of light, which allows us to use this as another astronomical tool in our toolbox. Okay, that is all I want to say about the interstellar medium. We're at 21 minutes. So what we will do next time is talk about the structures of spiral galaxies and other kinds of galaxies. We'll kind of situate our Milky Way in the landscape of different kinds of galaxies and maybe start to talk just a little bit about how galaxies might evolve and change over the course of their lives, which we're talking 10 billion years or so since the first galaxies formed. So that is what we will do next.